Hello. In the previous lesson, you developed EEPROM driver and tested its all three operations. In this lesson, you shall learn about interrupt-based EEPROM driver. We shall modify the earlier implementation to incorporate the interrupt-triggered write operation. In the earlier lesson, we disabled the EEPROM ready interrupt bit in the EECR register. If the bit is set, the EEPROM ready interrupt will be triggered constantly when EEPE bit is cleared. That means when the program starts, the microcontroller will be executing EEPROM ready interrupt service routine only, and the code in the main program is never executed. Note this point. It is important while designing the interrupt-based EEPROM driver. Before you make the changes in the driver, let's understand the design of the new driver. Since the EEPROM ready interrupt is constantly triggered, we shall keep it disabled most of the time. It is enabled right before any memory operation for checking if the operation can be initiated. Triggering of the interrupt indicates the operation can be safely started and the interrupt is disabled inside the ISR. A global flag keeps track of the busy state of the EEPROM memory. If it is set to 1, it indicates EEPROM is busy, else the operation can be initiated. The flag is checked before read, write and erase operations. Now let's implement the new driver. We shall reuse the code from the previous implementation. Copy the directory containing the driver code and name the directory as EEPROM_interrupt. First, add the busy flag in the EEPROM.c source file as shown. Define it to be static and volatile. Static as it must not be accessible outside the driver code, and volatile so that the compiler optimization doesn't change the code to retain stale state information. An unsigned character type is sufficient to hold the busy or free state. Define the function update_state as such. It resets the busy flag and disables the interrupt by resetting the EERIE bit in EECR register. This function is called from the interrupt service routine implemented by the application program. Add the function prototype in the EEPROM.h header file as shown. Then update the functions EEPROM_read and EEPROM_write. In the function EEPROM_read, just before setting the memory address in the EEARH and EEARL registers, enable the interrupt by setting the EERIE bit in the EECR register. Implement a busy loop using while, which checks the busy flag before proceeding to read the EEPROM memory. Then set the busy flag as shown. Remove the while statement which polls the EEPE bit as it is no longer required, and the rest of the functionality is same as the previous implementation. The same change is applied to the function EEPROM_write. Enable the interrupt, add a busy while loop and set the busy flag. Again, remove the while statement which polls for the EEPE bit. It is no longer required, and the rest of the functionality is the same as the previous implementation. There is no change required in the function EEPROM_erase. We need to completely change the implementation of the proc.c source file. Let me clean up the file. However, some of the code can be reused, like the #include statements to include the header files. Firstly, let's define the interrupt service routine for the EEPROM ready interrupt as such. The body of the ISR is defined as any other user-defined function. It calls the function update_state defined in the EEPROM.c source file. Add the function prototype. As it is an ISR, the prototype is defined with a few attributes as shown. These attributes were discussed in the section on interrupts. Please refer the section if you have any confusion. The reference to the ISR must be updated in the interrupt vector table that is defined in the interrupt.c source file. The 23rd interrupt vector corresponds to the EEPROM ready interrupt. Please take extra precaution to update the correct interrupt vector in the table. Now back to the proc.c source file. I shall implement two different functions to print the memory address and the data. The function print_EEPROM_address accepts the address as unsigned integer and returns nothing. The address is converted into ASCII string using the function _into ASCII hex and printed on the terminal using the function sprintS. Similarly, the data is printed using the function print_EEPROM_data. The function is defined as shown. Again, it accepts the address as an unsigned integer, reads the data by calling the function EEPROM_read and prints the data byte at the address. The data is converted into ASCII string using the function call _char to ASCII hex, and the function call sprintS prints the ASCII string on the terminal. Declare the prototypes of the functions as such. The function main is partially implemented. Let's complete it. The USART driver is initialized by calling the init_USART with the baud rate of 9600. Then initialize the EEPROM driver by calling the function EEPROM_init and pass the mode, that is erase and write. Declare the variables named address, data, index with the appropriate data types as shown. Let's program the entire EEPROM memory available in the Atmega 328 microcontroller. Implement a for loop to write the data as such and call the function EEPROM_write with the address and data. The EEPROM_size is a macro defined as such. The size of EEPROM in the Atmega 328 microcontroller is of size 1 kilobyte, hence the value 400 in hex. Add the prompt string to indicate the programming in progress for the user. Then loop for read the program data as such. The for loop prints the address of the first byte in new line followed by 16 data bytes. The address is printed only for the first byte in each line. The entire EEPROM memory is read and printed on the terminal emulator. The functions print_EEPROM_address and print_EEPROM_data is used to print the address and the data bytes respectively. A prompt string is added to indicate the EEPROM read operation in progress for the user. Now, the for loop that erases the entire EEPROM memory is implemented. The construct of the for loop is very similar to that used earlier. Then, copy and paste the for loop used to print the data content of the EEPROM memory, and finally end the function main with a return statement. The statement returns the value 0 as we have defined the function main to return an integer value. Check for any typos and error that compiler complains for. Launch the command line and compile the modified driver. Flash the development board with the command make flash. Connect the terminal, either TerraTerm or screen, and examine the statements. For me, the statement printed are as expected and the new driver works flawlessly. Both the driver design approach are equally good. Now it is up to the system designer to choose which one to use as per the requirement. I hope the section was helpful. Keep learning and bye bye.